Hi class, welcome to lesson 54. In this lesson, you are going to define and explain equilibrium, including phase equilibrium, solution equilibrium, and chemical equilibrium. Guided notes are provided, or you can take your own. Let's go. Let's start by defining equilibrium. Equilibrium is achieved when the rates of the forward and reverse reactions are equal and the concentrations are constant. Equilibrium looks like nothing is happening, but there is constant movement, so we call it dynamic equilibrium. So equilibrium can be physical or chemical, but all equilibrium occurs when two opposing processes occur at equal rates. Recall that rate refers to the speed at which a reaction or change occurs. So here's an example that can show you what we mean by equal rates. So as you can see in this animation, the person is bailing water out of the boat at the same rate at which water is filling into the boat. So we have two opposing forces happening at the same speed. How can we tell that they are equilibrium? Because the concentration or amount of water in the boat is constant. So if you start to bail water out faster than it fills in the boat, then the water level would go down. Or if you bail water out at a rate slower than it fills, the water level would go up. But here we are at equilibrium because the rate of removing the water is the same as the rate at filling the water, so the amount of water is constant. So systems at equilibrium look like nothing is changing. The overall net change is zero because the rates of the reaction are equal, but there is still constant change going on. They just are occurring at equal rates. When we have reversible reactions, we tend to use a double-headed arrow to indicate that the reaction can occur forward, in this case, water in to water out. We know this is forward because we read from left to right. And a reaction can occur in reverse or right to left, in this case, water out to water in. In order for equilibrium to occur, the processes must be reversible. So when we look at this simplified equation, we can see that the double-headed arrow indicates that the reaction is reversible. It does not indicate a reaction at equilibrium. But what this actually means is we have the forward reaction where reactant A forms B, and that is occurring at the same time when we have the reverse reaction where reactant B forms A. So the double-headed arrow does not indicate equilibrium, but having a reversible reaction is one of the requirements for equilibrium. Most of the chemical reactions we've done thus far have not been reversible chemical reactions at equilibrium because once equilibrium is reached, it appears that nothing is happening, although we know the rate of the forward reaction will always equal the rate of the reverse. So there are two major types of equilibrium. There's physical equilibrium and chemical equilibrium. We're going to start with physical equilibrium and look at phase equilibrium. So in this example, you can see an Erlenmeyer flask that when it has a stopper on it, it appears like nothing is changing. So if this flask is stoppered, which is really important when we have equilibrium, that it is a closed system, that the level of water will not change because the rate of evaporation should equal the rate of condensation. We know that if these rates are equal, then the total number of particles in the vapor or gaseous state should be constant, while the total number of particles in the liquid state will also be constant. So the concentration will be constant and will not change. So in this animation, you can see how equilibrium exists between the liquid and the gas phase. In this example, there are many more water molecules that are liquid than are gas. But as we see, for every one particle that evaporates, another one condenses. So we have two processes happening at equal rates. So we have both the evaporation of water and the condensation of water, and we can write this with a double-headed arrow. It is very important to note that phase equilibrium only occurs at specific temperatures and pressures. So here we have a kinetic energy diagram that shows the heating of water. And we can recall that at the plateaus, when the kinetic energy is constant, the potential energy is changing. So we have phase equilibrium at the plateaus of 0 degrees Celsius and 100 degrees Celsius. Solution equilibrium is yet another type of physical equilibrium. Do you remember what type of solutions can be at equilibrium? So the only saturated solutions can be at equilibrium. Do you remember why? Solution equilibrium occurs when the rate of dissolving equals the rate of recrystallization. So when we look here at this test tube with a saturated solution of calcium fluoride in excess, it looks like the amount of calcium fluoride at the bottom precipitated is not changing. But if we look really carefully at a microscopic level, we will see that the rate of dissolving is equal to the rate of recrystallization. So the common misconception in equilibrium is that nothing is changing, and that is not true. Instead, the rate of change is equal, so the amount that we observe, the physical amount, is constant. So we can write this reversible equation with a double-headed arrow. And if we begin with solid calcium fluoride and we dissolve it in water, it will be in equilibrium with 1 calcium ion and 2 fluorine ions. So since we've already learned about phase and solution equilibrium in previous units, in this unit we're going to focus on chemical equilibrium. Chemical equilibrium requires a reversible chemical reaction, and like all systems at equilibrium, the rate of the forward reaction should equal the rate of the reverse reaction. Here is an example of a system that reaches chemical equilibrium. This is the reaction where Hb is hemoglobin and O2 is oxygen. We know that hemoglobin and oxygen bond so that the hemoglobin can carry the oxygen around your body. This is the forward reaction. But we also need this reaction to go in reverse, to release the oxygen from the complex so that we can give oxygen to your cells to support cellular respiration. Now, the concentration of oxygen in our blood remains relatively constant. That means that this process is happening even though the concentration or amount of oxygen is not changing. Here you can see a chemical reaction that is at chemical equilibrium. As they heat this ammonium chloride, it produces ammonia and hydrogen chloride gas. But in the tube, it looks like nothing is changing. But when we look at a microscopic level, we can see that the forward reaction is occurring, or the decomposition of ammonium chloride to ammonia and hydrogen chloride gas. And the reverse reaction is the synthesis of ammonium chloride. Now, when we look at this reaction, we can see that it is an equilibrium because the amount of products and the amount of reactions are constant, even though there is an equal switch between the forward and reverse reaction rates. It should be noted that the amount of gases and solids is constant but not equal. So we have these two processes occurring simultaneously at equal rates. We can take these two equations and combine them together with a double-headed arrow to indicate that we have a reversible chemical reaction that could approach equilibrium. There are two major graphs used to demonstrate chemical equilibrium. Make sure that you copy both graphs in your notes. This first graph shows the relationship between reaction rate and time. Initially, the forward reaction in red occurs very quickly, but as the reactant particles collide to form products, its reaction rate slows down. Notice how the rate of the products in blue starts at 0, but it slowly increases until it has an even rate with the forward reaction. This highlighted region represents chemical equilibrium. So notice how the reactants in blue and green are slowly decreasing, and the amount or concentration of products in red are slowly increasing. The other graph that we use shows the change in concentration over time. In this reaction, notice that the concentrations of the reactants begin at their highest level, and then they start to level off as they collide to form products. Our reactants are in blue and green. The concentration of the products initially starts as 0, as no products are initially formed. But after the reactants collide, some products form. All of the lines become less steep and eventually they become parallel. Here, the concentrations are constant. This is a position of chemical equilibrium. So in summary, we can use graphs of rate versus time and concentration versus time to represent chemical equilibrium. Just like the situation where we are emptying a container as we are filling it, chemical equilibrium happens when the rates are equal and the concentrations are constant. As we said earlier, not every chemical reaction can reach equilibrium. In order to reach equilibrium, the chemical reaction must be reversible. It must occur in a closed system where no matter is added or removed, and it must occur at a specific temperature and pressure. Changes in temperature and pressure can cause changes in chemical equilibrium. Reactions that are not in chemical equilibrium are said to go to completion. Reactions that go to completion are reactions that produce gas. That means there is a gaseous product after or to the right of the arrow, and reactions that produce insoluble precipitates, like those found on reference table F. If you have a reaction that cannot approach equilibrium, again, the reaction is said to go to completion. Now take a minute to check your understanding. Are you able to define and explain phase equilibrium, solution equilibrium, and chemical equilibrium? This concludes lesson number 54, equilibrium. Make sure you've taken good notes, completed your homework, and you bring your questions to class. Recall that at equilibrium, the rates are equal, but the concentrations are constant. Things look pretty boring once they reach chemical equilibrium. That is because the physical characteristics like density or color will be constant, just like the amount of water in this water bottle will be constant once the rate of evaporation equals the rate of condensation.